Hello everyone, I'm Ruiwen from Zhejiang University. Today, I'd like to talk about our work on OK Siri or Hey Google, evaluating voiceprint distinctiveness via content-based ProScore. This is our agenda. First, I'm going to motivate our work and then talk about its challenging methodology. Then I will introduce how to define a ProScore and wrap up my talk with findings and conclusions. At the end of talk, what I'd like you to take away is to understand what content can improve the security of voiceprint. So, what is voiceprint? It's basically a memorable characteristic of a human voice. It is widely used in many scenarios, so the security of voiceprint is important. So, a very natural question is that, what is the security of voiceprint? In this paper, we focus on one aspect, which is distinctiveness. That is, given any two user, one will not be classified as the other. For instance, in a family, a normal case is Alice as a mom can control the smart speaker with granted voiceprint. And if the distinctiveness is low, her son Bob can impersonate Alice and use the smart speaker to play the rock music. That's what we don't want to see. So, what determines the distinctiveness of voiceprint? Recall the example in the previous. What Alice and her son says determines the voiceprint. So, if she says another phrase, "Hey Siri," does her son impersonate her voiceprint? This paper wants to answer the question, what types of speech content can provide secure voiceprint in terms of distinctiveness? Aiming at this goal, we contrast a voiceprint security scoring metric. For example, when you input the speech content "OK Siri," the scoring function will calculate the security score, give you a security level and some suggestions. And if you put "Hey Google," it will give you another score. And referring to the suggestions, we can generate more secure words for voiceprint. Actually, our security score is statistically related to the distinctiveness. That means high security score words like "OK Siri," its voiceprint will be low false recognition rate, where false recognition contains false acceptance and false rejection. A very typical scenario to use our ProScore is wake-up words. Smart speaker vendors spent much effort finding good wake-up words, and now most of commercial wake-up words consist of one or two words and with a prefix word like "OK Google." But are they actually able to provide enough distinctiveness in voiceprint? Our metric can help them to answer three important questions: whether their wake-up words secure, why they're secure, and how to improve them. So, how to contrast the scoring metric? We first investigate the automatic speaker verification system. Referring to the workflow, we can find the security of voiceprint is affected by all modules, including speaker, speech content, environment, and ASV module. So, how to get a ProScore while the user provides content but not the rest? The question actually to construct a universal score, it contains two challenges. One is the score should adapt to most of modules, speakers, and environment. That means the score will not tell you whether Alice and Bob have the same voiceprint in a certain module. It gives you statistical results. The other is the capability of handling the most of speech content. That means we can't measure it from the limited corpora. So the basic idea to generate the universal score is to use the statistical results of a large-scale measurement. In the measurement for a given speech content, we can get the statistical results of false recognition rate. We conduct our experiment with over 2,000 speakers and over 1,000 hour samples. We select three typical models, including classical and advanced models, I-vector, X-vector, and U-level, and believe they represent most of cases. And to adapt to most of speech content, we use the basic unit phones to compose of test audios with arbitrary content. We segment the whole audio to phone clips and reassemble them to test audios, so that over 14 million audios contain all kinds of phones. Our methodology can be divided into 3 key steps. We first analyze what phonetic factors we can derive from speech content. Then, to test the relationship between the content and distinctiveness, we construct a dataset that have general enough content and conduct a model fitting on the measurement results in this set to get the ProScore. Next, we introduce the component of the scoring metric ProScore. To study the effect of speech content, we look into it and represent speech content with some features. Since the phone is the basic unit of language, a sentence can be viewed as a sequence of phones. We define 4 phonetic factors: richness, length, element, and order. We take OK Google as an example, giving its phone sequence and phonetic factors. Then, we map the phonetic factors to security score. The scoring function has 7 variables, including 4 phonetic factors and 3 implicit variables. They are model, speaker, and environment. We call the output of function ProScore. So far, we get the input of ProScore, and then we are going to parameterize the function based on the statistical results of force recognition rate. It consists of 2 parts. One is the fact of single factor. The other is which factor is important. For richness, we give the statistical results of FAR and FRR on audios with different richness. We can find as the richness increases, the security increases as well, and when the richness is larger than 5, its impact is negligible. We can fit the impact as exponential function. We take Hey Google and Google as examples to show the difference in richness. We can find Hey increases the richness by 3. That has an improvement on security. So we get the finding the richness of content should be at least 5. For length, the statistical result is similar to that of richness. The difference is that when the length is larger than 13, its impact is negligible. We take 小度 and 小度小度 as examples. Repeating the word once increases the length by 7. So we get the finding. The content should be at least contain 13 phones. For elements, we give the sum of FAR and FRR on diverse phones, where having low bar means high security. We find some magic phones. They have low false recognition rate and better for generating voice print. For example, it is better than O in 3 typical models. We take 2 prefix words, OK and hello, as examples, and find O as a magic phone, so we had better choose more secure phones. For the last factor, order, we randomly change the order of phone A and phone B. Order has almost no effect on security. We can't consider order in selecting speech content. We also analyze the combination effect of 2 factors to ranking them. We find element is more important than length and less important than richness. According to this finding, we obtain the ProScore function by data fitting. With the ProScore metric, what can we do with it? One scenario is to help select the secure wake-up words. First, we answer the question whether the current wake-up words are secure. We assess 30 wake-up words from commercial products and calculate their ProScore on I-vector, X-vector, and U-level models respectively. We can get the following finding. The first one, we don't worry the richness because almost all wake-up words have enough richness. Even if the richness is enough, the length of most wake-up words is inadequate, so we suggest repeating once to improve the security. For example, repeating Alexa once as Alexa, Alexa, its security score increases by about 1. In addition, we find an interesting phenomenon. Chinese wake-up words prefer repeating like 小度小度. It may derive from linguist habit, but by coincidence, that actually improves the security. We find another interesting phenomenon. Most of wake-up words in English use a prefix word like hey or hello. Do they have an impact on voice print security? We compare the average ProScore of 7 wake-up words with or without prefix words and calculate the improvement in score. We find prefix words can increase the ProScore by around 24% because of its increased length, richness, and magic forms, and the better prefix words is okay. With the scoring metric, we develop a voiceprint security scoring tool and make it public on the website. Here we have a demo to demonstrate how to assess and select wake-up words. Possible users of voice assistants, such as manufacturers and customers, can select a model and input words to generate the score. As an example, we compare OK Siri and Hey Google mentioned in the title, and find OK Siri is better than Hey Google in generating secure voice print. To conclude, in this work, we proposed a scoring metric called ProScore to quantify the security level of speech content, especially for wake-up words. We assess 30 commercial wake-up words and review the behind reason whether they're secure or not. We developed an easy-to-use scoring tool to help manufacturers and users select secure wake-up words. In the future, we will study the effect of accent and improve the transferability of metric across models. This is my presentation. Thanks for your attention.